So let's start today's class. The class is Computer Organization Module 4, Lecture 4. Now,
ক্লাস শেষে আটটা শুরু হলো, তখন থেকে পরীক্ষা হলো, একটা ক্লাস শেষ হলো, আবার একটা ক্লাস শুরু হয়ে গেল।
Kindly mute yourself. So, in this class, in the last class, we learned about the pipeline. Okay. Now you know that to increase the performance of a system, we require the pipeline. What happens in the pipeline? In the pipeline, actually, the more than one instruction can be executed simultaneously. Okay, that means there is a partial parallel execution of the instructions. So here from this example, you can it will be clear that I have already told you. Suppose there are 3 instructions, okay, and the instructions are divided into stages. Here the stages S1, S2, S3, S4, and S5. 5 stages. So at first, in the first cycle, it will be I1. I1 will do the stage S1. Then in the second cycle, I1 will do S2 and I2 will do the S1. In this way, it will go, and this is the completion. That means it requires here, as there are 3 instructions and 5 cycles. So there will be 5 plus 3 minus 1. That means n plus s minus 1 total number of cycle is required if the execution happens in a pipeline. Okay. Now, if there is a non-pipeline architecture, the number of the cycle required n into s. That I have already told you. But the problem is if there is a branch instruction. If there is a branch instruction in the second case, what will happen? There is a penalty for the branch instruction. For each branch instruction, there is a penalty, and penalty is equal to number of stages minus 1. If the number of stages is s, penalty will be s minus 1. Clear? So here in this case, see here I2 is a branch instruction. So after the completion of I2, then only another instruction, it may be I3 or I4, can only be started. So otherwise it should be nope. Nope means the no operation. That means after I2, since I2 is a branch instruction here, after I2, processor cannot start any other instruction. Only after the completion of I2, processor will know what is the next address of the instruction, then it will start. That means next address of the instruction, if the next address of the instruction is I3, after the completion of I2, I3 will start. If the next instruction is I10, I10 will be started. So these are NOP, 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 NOP. These all are the no operation. That means this is the penalty. Here, this place, this, and all are at the NOPs. That means a no operation. That means processor cannot start any other instruction until the final address is determined by the branch instruction. And you know that the final address is only determined at the last stages. That means the memory write stage or the S5 stage here. Okay. Now see here, when the branch instruction occurs, processor has to remove all the subsequent instructions. That means processor has to stop the following instructions after the branch instruction. Okay. If the branch instruction starts. So that is called the hazard in a pipeline. Again, I repeat, if processor starts the following instructions after a branch instruction or any other instruction, processor has to stop the following instructions. So that phenomena is called the hazard of the pipeline. Here, one hazard is occurred due to the branch instruction. For this reason, processor has to stop all other instructions until the I2 is completed. Clear? That is called the pipeline hazard. Hazard means processor has to stop the following instruction due to some problem in the system. Clear? Problem means it may be the branch instruction or any other that I will discuss later. Clear? So that is called the pipeline hazard. That means due to the branching instruction, hazard will occur, and if hazard occurs, processor has to stop the instruction which comes after the branch instruction until the final address of the branch instruction is determined. Clear? Now, so here it is written, pipeline hazard prevent next instruction from executing during designated clock cycle. That means if pipelining hazard occurs, the next instruction after the particular cycle, that means it may be the branch instruction or any other instruction, it has to stop, and that is called the pipeline hazard. Clear? There are three types of hazard in a system. Okay, number one hazard is called the data hazard. Number two is a structural hazard. Another is the control hazard. Data hazard I will tell later. What is structural hazard? Structural hazard occurs. Hazard means processor has to stop the instructions. Okay, so structural hazard occurs from the resource conflict. What is the meaning of resource conflict? Structural hazard occurs due to the resource conflict. Here it is written. So what is the meaning of resource conflict? Resource conflict means, suppose same bus is used for memory read operation and memory write operation. Again I repeat, suppose the same bus is used for memory read operation and memory write operation. Now suppose there are two consecutive instructions which requires memory read operation, and there is another instruction which requires memory write operation. But as there is a single bus for this, next instruction has to be stopped because it is already occupied by the previous instruction. So as the next instruction is stopped in the subsequent cycles, that means that is a hazard from the definition of the hazard. So that type of hazard, due to the structure or organization of a computer, is called a structural hazard. Clear? Again I repeat, if the hazard occurs due to the lack of resource or there is a conflict in the resource in the system, that hazard in a pipeline is called a structural hazard. Clear? Next comes the control hazard. Control hazard example I have already given. Control hazard occurs due to the control instruction, that means branch instruction. As I have already told, or you have already seen, that if there is a branch instruction, processor has to stop all the subsequent instructions after the branch instruction. So that is the hazard, and that hazard, as the hazard occurs due to the control or branch instruction, the hazard is called a control hazard. The previous one was the structural hazard because due to the conflict of resources, as there is a lack of resource, the hazard occurs. So that is called a structural hazard. But here the hazard occurs not due to the resources but due to the branch instruction, because when branch instruction occurs, processor does not know what will be the next address of the instruction to be executed, whether it will I10 or I12 or I50. That means it can only determine the final address at the last stage of the branch instruction. So hazard will occur because after the starting of the branch instruction, it has to discard or flush out all the following instructions. So that is the hazard. That hazard is called a control hazard. Clear? Besides these two hazards, there is another hazard that is called the data hazard. It is very important. It occurs when given instruction depends on data from an instruction ahead of it in the pipeline. What is the meaning of that? It will be clear from here. Suppose this is the example of data hazard. Suppose there are two consecutive instructions, I1 and I2. Now what is the instruction in I1? The instruction in I1 is add A, B, C. C is equal to, the meaning is C is equal to A plus B. That means the data which is stored into the register A will be added up with the data in the register B. It will be stored in the register C. Similarly, add CEF means S is equal to C plus A. Suppose these two instructions is occurring in the pipeline. So I1, 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 then comes I2, 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 I2. Okay. But see, what is the problem? See here, the S3 stage is the memory read stage and S5 stage is the memory write stage. Okay, again I repeat, S3 stage, here S3 stage is the memory read and S5 is the memory write stage. Now the thing is, when this instruction occurs, see here, C will only get the data at the last stage. That means the S5 stage. Again I repeat, in the I1 instruction, C will generate the final data. That means the final result will be stored into the C, into the memory write stage. That means the last stage. Okay, but add CEF here, that means the data, I2 has to read the data from C and E, and it has to add the data and store the data into the F. That means I2 has to read the data from C, and this reading of the data will happen in the memory write state, which is the S3 stage. Clear? That means here when I2 comes in the S3 stage, clear, I1 comes in the S4 stage, not S5 stage. See here, again I repeat here, when I2 comes in the S3 stage, because S3 stage, it will read the data. Read the data means read the value of C and E. Okay. So in the S3 stage, I2 will read the data of C. But I1, which is the previous instruction, can only read the data, write the data into the S5 stage. That means in this, when I2 will read the data in the fourth cycle, I1 is not written the final data into the C. So what will happen? I1 will not get the final data written by I1. I2 will not get the final data written by I1. It will get the previous value of the C. That means previous means when the initial value of the C, when this A plus B was not happened, that value is taken by the I2. It will be clear from here. Suppose previously the value is C0, A is equal to 5, B is equal to 3. Okay, so I1, what will happen? I1 in the, if I execute I1, the data will be C is equal to 8. Okay, S is equal to 8 plus 2 is equal to 10. This is the normal calculation if no hazard occurs. Okay, but the problem is here hazard will be occurred because the data C will be written in the final stage. That means the S5 stage. That means in the fifth cycle. But S3 will read the data because S3 is equal to memory read. I2 will read the data into the fourth cycle. So which data I2 will get? I2 will get not the value of C as a 8. It will get the value of C as a 0 because C is not updated. C will only be updated at the last stage. That means the S5 stage, which is in the fifth cycle. See, in the I1 is in the fifth cycle, but here I2 will read the data in the fourth cycle. Which data it will read? It will read the data C as a 0. If it gets C as a 0, instead of C is equal to 8, the result will be 0 plus 2, 2. So what is the problem? See here, if I do in the pipeline, if I go the data in the instruction in a pipeline, the final data will be 2. But what is our expected data? Expected result, it should be 10 because after 8, it should be added with 2, it should be 10. But instead of 10, we are getting the result as a 2. That means that is the wrong result. So what processor have to do? Processor has to stop the instruction. Okay, which instruction? I2 instruction until I1 complete, just like the branch instruction. Clear? Again, I repeat, processor has to stop the instruction following the I1 instruction until I1 instruction completes and C gets is the updated data. C is equal to 8. That means here C will get the updated data. C is equal to 8. That means from here I2 can start. That means I2, 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 and all other things just like the branch instruction. It will be no. That is no operation. This, all will be no operation. Clear? So what is the reason for this hazard? So processor has to stop such that the result is correct. Otherwise, we'll get the wrong result too. Or our expected result is 10. So processor has to stop the following instruction. That means one hazard occurs here. So what is the reason of the hazard? Reason of the hazard is here in these two instructions. Here there is a common register. What is the common register? C. Due to this common register, there is a hazard occurs, and this type of hazard due to the following instruction where the one register is common or memory location is common, that hazard is called the data hazard. This is not a control hazard because it is not a branch instruction. This is not a structural hazard. That means this is not due to the memory read structure in the system. This is due to the as the two consecutive instructions has the same type of register they are using. That means the common register. So this hazard is called the data hazard. Clear? Now what is the mathematical analysis of the data hazard? See here. Here we have given add ABC, C is equal to A plus B. That's the previous example. Then add CEF, F is equal to C plus B. Now here we define for mathematical analysis, for mathematical analyzing the hazard, we define the domain of I1. What is the domain of I1? Domain of I1 is equal to, it is written as DI1 is the register where initially data is stored. So in this case, the right hand side A and B. So domain of I1 is A and B. Clear? And range of I1 is the register where final data is stored. What is the range of I1 here? C. That means range of I1 is C. So if this is type of instruction, domain of I1 is the register where the data is stored for the arithmetical or logical operation. Here in this case A and B, and range of particular instruction is R of I1 is the register where the final data is stored. Here in this case C. So here domain of I1 is AB and range of I1 is C. Clear? So for the next instruction, what is the domain? So for the next instruction, domain of I2 is obviously C and E. C and E, because C and E, here the data is added. So C and E. And what is the range of I2? Range of I2 is obviously F. Now the condition is one data hazard occurs if range of I1 intersection domain of I2, range of I1 intersection domain of I2 is not a null set. And that hazard is called read after write. That means there will be no hazard if only the data is read after the write operation. See here, in the previous case, there will be no hazard if data is read after the write operation. Write operation is done in the 5th cycle. Okay, if data is read in the 1, 2, 3, 8th cycle, that means after the writing of the data, there will be no hazard. So this type of hazard is called read after write. That means only after the write operation, if read operation is done, there will be no hazard. So this type of name of the hazard is called read after write hazard. So if range of I1 intersection domain of I2 not equal to null, this is not equal to null, that means there are some common set here, then one hazard will occur, that is called a read after write hazard. See here, what is range of I1? Here range of I1 is C, domain of I2 is CE. What is the intersection of range of I1 and domain of I2? C. That is not a null set. Null set means empty. This is not empty, so one hazard will occur. Okay, now see the second example. Add ABR I2 add CEF. Question is whether hazard will occur or no. Read after write hazard. See, range of I1. What is the range of I1 now? Range of I1 now is R. Domain of I2, what is the domain of I2? CE. What is the intersection of R and CE? Intersection of R and CE is null. That means there is no common register. So this is a null set. That means no hazard is occurred. Okay, that means if it is not equal to null, one hazard will occur, and there is a no null, not a hazard will occur. That means processor does not have to stop the instruction after I1 because there is no common register, and these instructions are sometimes called independent to each other. They are not dependent. I2 is not dependent on the I1. Previously, I2 dependent on the I1. Why? Because their register C is common. This data is taken here. But here R, this is a separate type of register. They are not related with C and E. So they are independent, and so no hazard will occur. That means range of I1 intersection domain of I2 equal to null. That means no hazard will occur. So this is the mathematical explanation of hazard. That means if two sets of register and instructions are given, you find out what is the intersection of range and domain. If you find that the intersection is null, that is no hazard occurs. If you find that yes, that is not null, there is some at least one register common there between two different types of instructions, two consecutive, not different, two consecutive instructions, that means one hazard occurs here, and that hazard is called read after write hazard. So depending on this, theoretically, mathematically, there are 4 types of data hazard, because there are 4 types of combination. What are the combination? Range of I1 intersection domain of I2 if not equal to null, hazard will occur. That is called the read after write hazard. That I have already given you the example. Similarly, it may happen that domain of I2 intersection range of I1. It may also happen. Okay. Hazard will occur. If it is not equal to null, hazard will occur. That is called write after read hazard. Similarly, if range of I1 and range of I2 intersection, there is a common value that is not equal to null, that is not an empty set, again one hazard will occur, that is the write after write hazard. Okay, and similarly, domain of I1 and domain of I2 not equal to null, another hazard will occur, that is called read after read. Remember, this problem occurs in a system only when there is a write operation. That means when we are updating something. If there is no requirement of updating or write operation, updating means write operation, then actually no problem occurs in a system. In this case, last case, read after write, this is theoretically a hazard, but practically it will not create any problem, because here domain means you are reading the data, you are not updating anything. Though it is a hazard, read after read hazard, but it will not create any problem in the system. And I think the processor does not have to stop if this occurs, because it will not, there is no clash between the different type of register. If I read this, we're not changing that, we are just reading the data. Clear? So this is called read after read hazard. So these are the different types of hazard. So this is actually the pipeline. Pipeline means here we, in the pipeline, we increase the speed of the system by the overlapping execution of different type of instruction. So we know that if the non-pipeline processor, the total number of cycle is n into s. N is the number of the instruction, s is the number of the stages in the instruction pipeline. If this is a pipeline without branch instruction, the number of cycle will be n plus s minus 1, and speed up will be ns by n plus s minus 1. Last day I have told, if there is a branch instruction, we require one penalty. Penalty is less than the number of stages. That means s minus 1 penalty is required for each branch instruction. If there are nc number of branch instruction, where n is the number of the instruction and c is the probability of branch instruction, so what will be the number of cycle? Number of cycle is s plus n minus 1 plus nc into s minus 1. The formula I have told last day. Okay. So after that, this is called the hazard is due to the branch instruction. Similarly, there are two more hazard. One is the data hazard. I have told you data hazard had the 4 types of hazard, and there is a structural hazard. Structural hazard is occurs due to the clashes in the different resources in a system. So these all about the pipeline. Clear? Now this is the new thing, that is the architecture of a CPU. We know that when we learn about the different thing, we know that there are pipelining in a system, there are different types of memory, operating system, okay, virtual memory, cache memory. Then comes the design of the control unit. There are 2 types of design, mainly the hardware design, hardware control unit, and microprogram control unit. So here remember, and there are different type of instruction set depending on the different types of addressing mode. Okay, so remember that all the things are not used in the all types of machines. Okay, depending on the architecture, mainly there are 2 types of architecture which use different types of things. Okay, so these 2 types of architecture is called the RISC. The full name is the reduced instruction set computer. From the name it is clear that here the instruction number of the instruction is low. Reduce means the simple. Okay, reduced instruction set computer. And another is the complex instruction set computer. All the Intel, see, in the reduced instruction set computer, the example is IBM RS6000 and MC88110. These are the processor which use the reduced instruction set computer. Okay, and another is the CISC, that is the complex instruction set computer. Complex instruction set computer means here Intel and all the families of the Intel. That means Intel 8086 to Pentium Pro 2, 3, anything. They use the complex instruction set computer. Now the thing is, what are the difference between these 2 types of architecture? Okay, the main difference comes from the control unit. Remember that in the RISC actually uses hardware control unit. Again I repeat, RISC, that means the reduced instruction set computer. The example is the Intel. Example is the IBM RS6000. This uses mainly hardware controlled control unit. Clear? Where CISC uses the microprogram control unit. 6 type of architecture actually uses the microprogram control unit. This is the broad difference. Now RISC has some features. So what are the features in the RISC? RISC processor use small and limited number of the instructions. The instructions in the RISC are small, they are limited. Okay, and there is no complex type of instruction. Their instruction is very easy to understand. Clear? RISC machine mostly use the hardware controlled. I have already told you RISC uses the hardware control unit, not the microprogram control unit. Okay, so RISC processor consumes less power and are having high performance. Each instruction is very simple and consistent. Consistent means their length of the instruction is almost same in case of the RISC. In case of the RISC, there may be vary. Okay, but in the RISC, the instruction are very simple and consistent. Clear? RISC uses the simple addressing mode. The addressing mode is simple. There is no complexity in the addressing mode. You can easily find out what is the addressing mode from the instruction. Okay, and this instruction is of uniform fixed length. That means if the length of the RISC instruction is, if it is a 10-bit machine, the length of the instruction will be 10. It will not change. But in case of the RISC, the length of the instruction may be changed. Suppose some instruction is 10-bit, some instruction is 12-bit. So it is very difficult to decode. From this, you know that it is very difficult to decode if you use the different types of different length of the instruction. Though RISC has the many advantages. Okay. So here RISC is actually use the microprogram control unit. I have already told that most of the modern machines use microprogram control unit. Why? Because microprogram control means it is a software controlled, and always remember that if the system is software controlled, so here it is a more flexible than the hardware control unit. So that is the greatest advantage of the RISC. Clear? Otherwise, RISC has a large amount of different and complex instructions. Though Intel is very popular, Intel actually uses the RISC instruction. Okay. Now RISC machines generally use of the complex addressing mode. Instruction is complex. Obviously, addressing mode are very types of complex. That means it uses different types of indirect addressing mode. Remember that the addressing mode is indirect if any type of processor uses the indirect addressing mode. The type of the instructions will be very types of complex instruction. Okay. Different machine program can be executed on the RISC machines. That is okay. RISC machines uses the microprogram control unit. Okay, and RISC processor have a limited number of the register. Okay, in case of the RISC processor, the number of the register is very high because you have a limited number of the instruction. I have already told in the RISC. Though they are simple, they are limited number of the instructions. So they have to use more registers. Okay. But here in the RISC, there is a complex type of instruction. That means in the one instruction, you can do more than one work. So your requirement for the register is low in case of the RISC. Okay, this is the advantage of using RISC. Though in the modern machines, there is some combination of RISC and RISC. Clear? So this is the feature of the RISC. You have to actually remember what is RISC, what is RISC, and what is the difference between the RISC and RISC. It will be clear from this slide. Clear? So that's all for today. And here I stop.